So I want to go through an example here about calculating the change of energy of a liquid as it's boiled into some superheated vapor state. In this case, I just have an example where we have some water. In this case, we have water in a pot at 40 degrees Fahrenheit, and we know that water freezes at 32 degrees Fahrenheit, so at this temperature, it's a liquid. And then we heat it up to a total of 300 degrees Fahrenheit, which is beyond the boiling point of water. So in this case, we're producing some sort of vapor or producing steam. And this is all run at 1 atmosphere, so standard pressure. So we want to know what is the energy difference between the steam here at 300 degrees Fahrenheit and this liquid water at 40 degrees Fahrenheit. And there are two different ways that we could do that. First, so method 1 is to look up information on the steam tables. So we might look up U1 and U2 being the internal energy at the final state. So I could look up 300 degrees Fahrenheit and 1 atmosphere or 1 bar and look up the U value for that, U2. And then I could also look up, and there's a section under there for subcooled liquids, and I could look up 40 degrees Fahrenheit, and again atmospheric pressure for U1 here. And I could just take the difference between the two to find out the change in internal energy going from this 40 degrees Fahrenheit up to 300 degrees Fahrenheit. So that's one way. Let me talk to you about another way. The other way involves the heat capacity and the latent heat of vaporization. So I just drawn here just a line showing us the temperature as we're going from this initial state here to this final state here. So what happens? Well, if we start at 40 degrees Fahrenheit, we add some heat into our system, and it gets hotter and hotter and hotter and hotter and hotter and hotter until it gets to 212 degrees Fahrenheit. And what will happen is that the liquid, the water in the pot or in the container we have, will boil off, and then once it's all boiled, it will continue to rise in temperature up to 300 degrees Fahrenheit. And we can calculate the energy it takes for each one of these different segments. And the way we go about doing that is to use information about heat capacity and also latent heat of vaporization. So the formula that I would use to calculate the change in internal energy is listed right here, this big long equation here. And it's the specific internal energy, so this is on a per mole or per mass basis. So we just need to take that into account. If we want to convert it to just a normal amount of energy, we need to multiply it by number of moles or mass, depending on the units of these parts over here. But each of these different parts here corresponds to different changes here. This first integral right here represents the energy it takes to go from temperature 1 to temperature 2. So in other words, heating up at 40 degrees Fahrenheit and getting up to 212 degrees Fahrenheit. And this is the heat capacity of liquid water. Typically, liquid water has a constant heat capacity. It doesn't change much with temperature, so oftentimes we'll just, again, take this outside the integral, and it gives us a much simplified expression. But this whole part right here tells us the energy difference between this final temperature, T2 of 212 degrees Fahrenheit, and 40 degrees Fahrenheit. And once we get up to 212 degrees Fahrenheit, we are a saturated liquid, and if we add enough heat, we'll eventually boil off and get all vapor. And that's represented by this value right here, or the heat of vaporization, or latent heat of vaporization. And that's just simply the energy it takes at 212 degrees Fahrenheit to go from a saturated liquid to a saturated vapor, or to boil off all of that liquid to form the vapor phase. And then finally, once we're a vapor at T2 or 212 degrees Fahrenheit, we're going to keep adding, we're going to need more energy to get us up to T3 or 300 degrees Fahrenheit. And that's represented by this integral right here. The difference between this integral and this first integral is that this right here, heat capacity, it's the heat capacity of steam or vapor water. So it's going to be a different heat capacity. The heat capacity of liquid water is very different than the heat capacity of vapor water. So we would just put in the heat capacity of vapor, water, or steam into this equation and evaluate it, this integral here. So in summary, each one of these different parts here just gives us the total energy difference between different segments here, T1, T2, and T3, as we're going along from 40 degrees Fahrenheit up to 300 degrees Fahrenheit. And we just have to keep the different parts in mind. We have to realize, for instance, heat capacity of liquid only applies to the liquid phase, so we can't apply that heat capacity beyond 212 degrees Fahrenheit at atmospheric pressure. The heat capacity of steam also only applies for the steam. And then to take into account the transition between the liquid and the vapor at 212 degrees Fahrenheit, we have to add in the heat of vaporization component right there. And that's it, just an example of how we can evaluate energy differences between two different states of this material, in this case water, using either steam tables or formulas such as this that's based on heat capacity and so forth. So, thank you.